Good morning. Today we are going to look at lesson 2-3 in quantitative reasoning, and the title is 88 miles per hour. You should be on page 157. And back in an earlier lesson in Unit 1, we talked about rates of unit rates. And so now we're going to talk about rates of change. So the quote says, the future is something which everyone reaches at the rate of 60 minutes an hour, whatever he does, whoever he is, C.S. Lewis, which means we all have the same amount of time in a day. Anyone familiar with the classic movie Back to the Future instantly recognizes the significance of 88 miles per hour. It's the speed the DeLorean time machine needed to reach in order to travel through time. Speeds like 88 miles per hour are familiar examples of the topic of this lesson, rates of change. Our world is a dynamic, ever-changing place, so studying the rate at which things change is an excellent way to study the world around us. The amount your grade changes as you spend more time studying, that's a rate. Your hourly wage if you work a part-time job, that's a rate. A waiter's decrease in tips as fewer customers eat at a restaurant, that's a rate. They're everywhere. Fortunately, studying rates will tie together some of the skills you've already practiced in this course, meaning we're in a good position to make the most of this useful topic. So a rate is a ratio that compares two quantities. This is an important one to know right here. A rate is a ratio that compares two quantities. And we did this back in Unit 1. By rate of change, we mean a rate that compares the change in one quantity to the change in another. A speed like 88 miles per hour qualifies because we can write it this way, 88 miles for every 1 hour. This quite literally compares a change in distance, 88 miles, to a change in time, 1 hour. That's exactly why we measure speed in miles per hour. The word equivalent is an important word in math and one that we'll use often in this course. Make sure you clearly understand what that word means. For our purposes, we'll say that two quantities are equivalent if they have the same value or are interchangeable, even if they look different. If you make $100 a day for doing a certain job, how much money would you make in a 5-day work week? I would say $100 times 5 days for 1 day times 5 days gives me $500 using our unit conversion we did back in Unit 1. So number 2 says, are $100 per day and $500 for 5 days equivalent rates? And what does that mean? So I would say yes. And that means that they can both be made into the same unit rate. They both simplify to the same unit rate. So on page 158 here, it says, question 2 demonstrates a useful fact about rates of change. They can be scaled up or scaled down to fit a given situation. Scaling up a fraction is done by writing an equivalent fraction, that is one that has been the same value, using larger numbers. Scaling down is writing an equivalent fraction with smaller numbers. These processes are done by either multiplying both the numerator and denominator by the same number or dividing both the numerator and denominator by the same number. So number 3 says, write a fraction equivalent to 60 miles over 4 hours that has 2 in the denominator. So 60 miles over 4 hours. And they want something equivalent that only has 2 in the denominator. So what would we have to do from 4 to get to 2? We would have to divide by 2. So that means we also have to divide by 2 so that we're dividing by a perfect 1, which is, this is the equivalent fraction we're going to use for 1. So we divided by bottom, the denominator by 2 to get to 2. 4 divided by 2 is 2. So that means if we do 60 divided by 2, we get 30. So that would be an equivalent fraction. 4 says write a fraction equivalent to 60 miles over 4 hours. It has a 1 in the denominator, a rate of change with 1. This is a unit rate, which we did back in unit 1. So 60 miles over 4 hours. And we want it to have 1 hour here. So in order to do that, we would have to divide the denominator by 4, which means we have to divide the numerator by 4. 60 divided by 4 is 15. So we can drive 15 miles in 1 hour. Now, number 5 says, write a fraction equivalent to $320 for 4 days that has 10 in the denominator. First, scale down, then back up. So 320 over 4. So our goal is to have 10 in the denominator. Now, 10 is not an even multiple of 4. So it's easier if we scale this down to 1 and then multiply by 10 to scale up. So if we scale this down to 1, we're going to divide by 4. 4 divided by 4 gets me to 1. So I'm going to divide my top by 4. And then using Desmos or calculator, 320 divided by 4 gives me 80. So now that I have a unit rate, I can now multiply by 10 over 10. Remember, they always have to be either dividing by equivalent of 1 or multiplying by equivalent of 1. And that gets us to $800 over 1 times 10 for 10 days. So number 6, if one bicyclist is pedaling at a rate of 40 miles in 3 hours and another at a rate of 50 miles in 4 hours, which is faster? Scaling either up or down can be used. So, and so let's look, we have 40 miles in 3 hours. And I'm going to scale down to get them both to a unit rate. So that means I'm going to divide by 3. 3 divided by 3 is 1. And then it forces me to divide by 3 on top. And so using a calculator, 40 divided by 3 is 13.3. Now to be able to compare these, we have to make sure that we've got our units. So that's always very important. And then over here, we're going to have to scale down. We're going to have to divide by 4. And so a fraction of 4 over 4, so 50 divided by 4 is 12.5 miles in 1 hour. So we have to decide, is bigger better or is smaller better? So let's see, it's asking us which is faster. So who can go more miles in the same amount of time? So in this case, this bicyclist over here, because they can travel 13.3 miles in 1 hour, whereas this bicyclist can only travel 12.5 miles in 1 hour. Okay, let's move down to the bottom. It says most experienced runners get to a point where they can comfortably jog long distances at a consistent pace. This pace, of course, is another way to say rate of change, because speed is the rate at which distance changes compared to time. One particular runner jogs 1 lap around a 400-meter track in 2 minutes. So in the rest of the question, 7 through 16, you can assume that the runner can maintain this pace for a long time, okay? So for every 2 minutes, the runner jogs 400 meters. Complete the table, continuing the pattern for times and finding the associated distances for this runner. So in 2 minutes, they can jog 400 meters. So if we double the time, we should be able to double the distance. so 800 meters. So again, if we double from 4 hours, so for every 2 minutes, they're going 400. So it looks like we're doubling, but it's really an addition. Because this rate, so if we add 2 minutes and 2 more minutes, at 6 minutes, they should go another 200 meters, which would be 1,000 meters. I meant in 2 minutes, I misspoke. They go another 400 meters, which should be 1,200 meters. Because remember, we could write this as 400 meters for 2 minutes and get a unit rate to help us out. So if we divide by 2 over 2, we find out for every minute they go 200 meters. So in 2 more minutes, at 8, they go 400 more meters, which would be 1,600. Okay, and 2 more minutes, they go another 400 meters, which would be 2,000. Okay. And we can continue this. You could continue and do this in Desmos as well, because Desmos sees a pattern. So in 2 more minutes, they go 400 more meters. So we're going to use this to help us answer questions on page 159 here. It says, notice that the rate at which the runner's distance changes is constant. When the rate of change is constant, a quantity illustrates what type of growth that we encountered earlier in this unit. So rate of change is constant, and we were adding a constant value, which means we have linear growth. Write the runner's rate as a fraction using meters in the numerator. So we said it was 400 meters for 2 minutes. We knew that as a fact. Write this rate as a unit rate in meters per minute, which we did on the prior page. So 400 over 2, we said if we divide the top by 2 and divide the bottom by 2, we'll get 200 meters over 1 minute. Now we're in a unit rate. Convert your rate from question 11 to meters per second using dimensional analysis. Okay, so 200 meters, 1 minute. So they want meters per second. So we don't have to change our length. So we're staying with meters, but we want to switch to seconds. So the only thing we have to exchange is minutes. So we know in 1 minute, minute has to go on top because we're canceling minutes out, is equivalent to 60 seconds. And we wanted meters over seconds, so that's good. So we multiply straight across, we get 200 over 60. And then we're going to divide 200 divided by 60 is 3.33 repeating meters per second. What distance will the runner cover in 40 minutes? So in minutes, that means we have to use the unit rate that we know that's 200 meters per minute because we're talking minutes. So 200 meters in 1 minute, and they want us to build this up to 40 minutes. So we're going to build up our fraction. right, what we're doing, build fraction up. So to do that, what can we do to get from 1 to 40? We can multiply by 40. So we have to multiply the top by 40. So 200 times 40 gives us 8,000 meters. Number 14 says, what distance will he cover in 40 seconds? So I'm going to use the unit rate for seconds because I want to build up to seconds. So 3.33, we can round that to meters for 1 second. And we want to build up again to 40 seconds. So again, we're going to multiply by 40 over 40 because we're building up 1 to 40. And we get about approximately 133.2 meters in 40 seconds. Based on the previous two questions, can you write a formula for finding the distance traveled by an object when you know the speed and amount of time traveling at that speed? So can you write a formula for finding the distance? So distance equals, because they were in unit rates, we really didn't have to do anything with our denominator. So we could say, it looks like knowing what you want your new time to be, you're essentially just taking your unit rate and multiplying by time. And distance equals rate times time is a formula that you might use in other classes. So last question here. It says, what would this runner's total time be for a 10K race? 10 kilometers, that is. 1 kilometer is 1,000 meters. Your answer to question 11 will help. Okay, so we need to find out what they're traveling for. So we know 1,000 meters. So a 10K race is the same as, we got to figure out how many meters we have in a 10K race. So 1 kilometer is 1,000 meters, but we're going 10K. So it's really 10,000 meters, right, is my distance. And I know this to be true. Distance equals rate times time. And I know my distance this time. And I know my rate that I travel at is 200 meters per 1 minute. 200 meters per 1 minute. But I don't know time, right? And I want to go 200 meters, or I want to go at 10,000 meters. And I know for every 200 meters, I'm traveling 1 minute and I want to solve for this time. So I can divide both sides by 200 to solve for t. So if I do that, my 10,000 divided by 200 says it'll take me 50 minutes. So it's 10,000 divided by 200 will be my time. It'll take me 50 minutes. So that is the end of lesson 2-3, part 1, and I'll see you back for lesson 2-3, part 2.